A very good day. I would like to greet everyone. Today, me, LEKHA ARUMUGAM, and my friend NADHIRAH KAMARUDDIN will be presenting on in silico analysis of 𝘴𝘪𝘭𝘪𝘤𝘰 chordata active compounds against SARS-CoV-2 main protease, which is known as mpro and helicase. Starting off with introduction, COVID-19 is caused by SARS-CoV-2 virus that has been spread rapidly all over the world. There are many vaccines currently available, which includes Pfizer, Sinovac, AstraZeneca, Sinopharm, and Johnson Johnson. Although there are many vaccines available, this virus has many variants as well as a high mutation rate which cause it to escape the natural or vaccine-induced immunity. Hence, therapeutics targeting the SARS-CoV-2 RNA synthesis and replication plays an important role in the development of the multi-targeted treatment options for COVID-19. Hence, this study evaluated the binding interactions of 𝘴𝘪𝘭𝘪𝘐 chordata active compounds and SARS-CoV-2 Mpro and Helicase using the molecular docking approach. 𝘴𝘪𝘭𝘪𝘐 chordata is a plant that has said having an immunomodulatory and anti-SARS activity against the previous SARS-CoV virus. This plant was used in the study to see whether it exhibits similar effect on SARS-CoV-2. The objective of the study is to study the interaction of 𝘴𝘪𝘭𝘪𝘐 chordata active compounds against SARS-CoV-2 main protease and helicase using molecular docking approach based on the lowest free binding energy of the most populated cluster and the binding interactions between the protein and ligand. Moving on to the methods that were used in the study, the first method was ligand and protein preparation. A total of 20 active compounds were selected from 𝘴𝘪𝘭𝘪𝘐 chordata and the structures were downloaded from the PubChem, whereas Mpro with the protein data bank ID of 7BQY and helicase with the protein data bank ID of 6ZSL that were used as targets in the study were downloaded from the protein data bank using the protein data bank ID. The second step was molecular docking. Both protein and ligand were subjected to molecular docking using AutoDock 4.2.6. Lamarckian genetic algorithm was used as the primary conformational search algorithm throughout the docking stimulation. The docking output were presented in terms of free binding energy and numbers in cluster. The interaction between the 𝘴𝘪𝘭𝘪𝘐 chordata active compounds and SARS-CoV-2 Mpro and helicase were studied using the protein-ligand interaction profile. Here are the structures of the targets, 𝘴𝘪𝘭𝘪𝘐 chordata compounds and controls that were used in the study. The control that was used for Mpro was N3 and the control that was used for helicase was bismuth potassium citrate.
This table shows the result of the three compounds with lowest binding energy of the most populated cluster for Mpro and helicase. Free binding energy plays an important role to create a higher binding affinity of ligands towards the target. Based on our result, it was shown that the best three compounds interact with Mpro. For protease, these are the compounds shows that to have the lower free binding energy than the control N3, which is 𝑘-amphorol, epsilene, and acetylcysteine. Whereas in helicase, shows slightly higher binding free energy than control itself. The more the binding interaction, the stronger the interactions between the 𝘴𝘪𝘭𝘪𝘐 chordata compounds with the target would be. This is the interactions that involve between three best compound of 𝘴𝘪𝘭𝘪𝘐 chordata with Mpro. We can see that the interactions involved in the formation of hydrogen bond, hydrophobic interactions, and also few other interactions such as pi stack interactions. 𝘏-amphorol has a total of 6 hydrogen bond, 5 hydrophobic interactions, and a pi stack interaction, which is the highest in total compared to other 𝘴𝘪𝘭𝘭𝘐 chordata compounds such as epsilene and acetylcysteine. This indicates that 𝘏-amphorol has the strongest affinity against the Mpro. This is a diagram that showed the result of molecular docking from molecular analysis. The blue structure represents Mpro and the golden orange structure represents 𝘏-amphorol. It shows all the interactions that form between Mpro and 𝘏-amphorol. Based on this result table, the control for helicase, which is bismuth potassium citrate, shows to have the strongest binding affinity and the highest interactions involved with helicase compared to other 𝘏𝘪𝘏𝘧 compounds such as saprophyrin B and quercetin. Thus, it shows that bismuth potassium citrate has the strongest binding affinity against helicase. These are diagrams from molecular analysis that shows the difference in interactions involved between bismuth potassium citrate and saprophyrin B with helicase. There are more interactions forces involved in helicase control structure compared to saprophyrin, which makes it to have the strongest binding affinity towards the target. Based from the result we obtained, 𝘏𝑚phorol, 𝑓-xylene, and ascoquercetin are the most potential compounds for Mpro. To support this result, previous studies had shown that 𝘏𝑚phorol, ascoquercetin antiviral effects towards SARS coronavirus and also cytomegalovirus by suppressing the viral genes, whereas some alkaloids have antiviral effect against herpes simplex virus type 1 by interfering the viral replicative cycle. Quercetin, which is a flavonoid, it inhibits influenza virus by reducing mRNA transcription in dose-dependent manner, and it inhibits rhinovirus by blocking the endocytosis via P1-3 kinase inhibition. All these interactions involved in protein and 𝘏𝘪𝘏𝘧 compounds are necessary for the protein folding and stability, and also to remove all the water molecules involved. Hence, these interactions plays an important role on the free binding energy and also for the binding affinity. Based on our research, we conclude that flavonoids and alkaloids might bind against SARS-CoV-2 Mpro and Helicase. However, further research studies might be needed to support our findings. These are some of the references involved in this study research. Thank you.